right, let's get started. Welcome to Barcelona, welcome to NIPS, welcome to the second tutorial of the day, which will be on nuts and bolts of AI using deep learning. And it's my great pleasure to introduce Dr. Andrew Ng, who needs no introduction, as is often the case, but I will go through the motions. Dr. Andrew Ng joined Baidu in 2014, most recently, as a chief scientist, and he leads Baidu AI in Beijing and Silicon Valley, and leads technical teams in the areas of speech, big data, and image search. In addition to his role at Baidu, Andrew is also an adjunct professor at Stanford University. And previously, Andrew was the founding lead of the Google Brain project, which has also been very influential. Dr. Andrew Ng holds degrees from Carnegie Mellon, MIT, and the University of California, Berkeley. Please welcome him and enjoy the tutorial.
Thank you. Thank you. Thank you. Is this turned on? Okay, awesome. Thank you, Raya. I'm curious, for how many of you is this your first time ever attending a NIPS conference? Raise your hand. Holy cow, wow. Well, welcome to all of you. I'm excited to see that NIPS is growing so rapidly. So as I was preparing for this presentation, I spent some time trying to figure out what would be most useful to all of you in this audience. And, and I want to, it occurred to me, I think I've worked in AI for a long time. And the reason I'm excited about AI, machine learning, deep learning is because of the impact it can have. And as AI, machine learning, deep learning is evolving rapidly, the methods and the processes we use in order to take our research work, to take your research work, and go and have an impact, build applications, build products, is evolving as well. And what I want to do today is to share with you the best practices I'm seeing across the many teams that I've led or had the privilege to nurture in terms of how we're able to take state-of-the-art deep learning algorithms, such as you might learn about over the next few days at NIPS, and use it to go beyond the research paper to building an application or product or shipping something that really matters to hundreds of millions of people. So to those of you that are on the corporate side, for those of you that work in companies or build a startup or work on applications, a lot of the ideas I talk about today will seem very simple, but I can promise you that they are important, right? And in that, if you apply some of the practices I shared today, I can almost guarantee that you or your team will be more effective at taking deep learning algorithms and driving them into practice. After my flight landed in Barcelona last night, I checked into Hilton Hotel, got an email, and literally last night I got an email from one of my directors talking about one of Baidu's partners, not Baidu, but a different company, that I believe they've been working on a 6-month project, and they just found out, yesterday that what they did was not going to work. And the way their process was broken is something I'll talk about today. So frankly, if they had heard this presentation 6 months ago, they would have saved themselves a lot of work. And so I hope that for those of you on the corporate application side, that the things you learn will have that impact on your work or your team's work as well. To those of you on the academic side, what I'm going to talk about today is much more practical, much more applied, and frankly, less academic. If you're in academia and if you want to learn how to apply these things to concrete applications, in science or industry or whatever, some of what I'll say will be useful. But for those of you on the academic side, I hope to also have you maybe see some of the messiness, the messiness of the sausage being made of how we take the nice research papers and turn it into impact. And maybe some of the talk about will maybe help you with some applications, but maybe also inspire some of you to develop new theory to clean up, frankly, some of the messy practices I want to describe today. So as Ryan mentioned, I lead Baidu's AI team. It's about 1,300 people working on speech, natural language processing, computer vision, run image search, keyboard products. I own Baidu's big data warehouse. So I've been fortunate to touch a lot of machine learning projects. And when I was trying to decide what to include in, what to share with you in today's presentation, what I wanted to do was try to find the common patterns I see across many of the machine learning projects that I'm glad that I get to support. And so that makes me quite confident that the patterns I see will be useful to a lot of you as well, since these are patterns I've seen that are common across many, many machine learning applications. And so the outline is that we'll talk a little bit about major deep learning trends. This will be really quick. Talk about the rise of end-to-end deep learning and how you can fit that into your work. Do a recap of bias and variance. And we all learned about bias and variance, but I feel like in the modern deep learning era, the way we think about that is changing. Talk about mismatched trained test sets. This is another problem that is relatively little studied in academia, but that is one of the most critical problems we run into all the time when trying to ship products. Talk about how AI is changing product management, and then maybe give personal advice to each of you that wants to get better at AI and machine learning. And one of the themes of this is that the workflow of how we organize teams and our machine learning work is very different in the deep learning era. So share with you some of those changing practices. And one more warning. So I was talking to my wife, Carol, on Saturday, and I was showing her the notes I had put together for this presentation. And so she flipped and said, "Wow, Andrew, there's like no math in this." And I said, "Yeah, I'm a little insecure about that." And my wife kind of laughed and laughed and laughed. But there isn't, today's content is actually not very mathematically technical, but I think the concept is actually difficult. But I hope that you take that away from you and have many things that you find useful for things you might work on, say next Monday after you get home after NIPS. Okay? So, all right, let's dive into it. A lot of hype about deep learning, right? We all know it's the latest, hottest thing in AI. It turns out a lot of the ideas in deep learning have been around literally for decades. Not all, but many of the ideas have been around literally for decades. So why is deep learning taking off only now? I get asked that question a lot. And when I'm asked that question, there's one picture that I always draw to try to explain why deep learning is taking off now. And if you are ever asked that question, perhaps you draw the same picture for people asking you as well. But this is the picture I draw, which is if on the horizontal of this axis, we plot the amount of data we have for a problem, and on the vertical axis, we plot the performance of a learning algorithm, then it turns out that if you apply, the older generations of learning algorithms, the performance kind of goes like that, right? So, let me say traditional ML, like logistic regression, support vector machines, maybe decision trees, 13 years neighbors or whatever. But it's almost as if for the older generations of algorithms, their learning capacity, you can say VC dimension, mathematical complexity or whatever, but somehow wasn't high enough to capture value in the huge amounts of data we have. And over the last 20 years, with the digitalization of a society, as all of us start to spend more time on mobile, first desktops and laptops and mobile devices, our society has been marching steadily to the right of this curve, but the older generations of algorithms just weren't able to keep doing better, even as we fed it more data. And so, while there are many reasons for the rise of deep learning, what we started to find a few years ago was that, if you train a small neural network, maybe you get slightly better performance. If you train a medium-sized neural net, maybe it works even better. And if you train a very large neural net, then the performance kind of keeps getting better and better for a lot of problems. And so I believe that the number one driver, the number one reason really for why deep learning is taking off now is scale. And the scale of two things. Scale first of data, right? And second, scale in the size of the neural networks they're now finally able to build. So in order to hit the highest levels of performance to get way up here, you want to be on the green curve. So you usually need to train reasonably large neural networks as measured by number of parameters, hidden units or layers or whatever. And having very large data sets also helps. And One caveat, right? I drew this diagram as a maybe simplified diagram. The relative ordering of the algorithms in the small data regime is not well defined. I guess I drew this picture as if large neural nets always do better, but in the small data regime, if you have if you have computer vision problem with 20 training examples, then it really depends much more on your hand engineering skill or your skill at manually picking features, what algorithm works better. If you give me 20 training examples, I bet I could hand engineer features so that k-nearest neighbors outperforms the neural network or something, right? Depends on who's more motivated to hand engineer features better, but it's really in the large data regime that the rank ordering of these algorithms becomes much more apparent. Because of this trend as well, one other impact of this is that seeing a trend toward AI teams now being built like this. We have a machine learning team, and the machine learning team actually comprises kind of distinct subsets, with part of the team responsible for the deep learning algorithms and part of the team responsible for computer systems. Because what I'm seeing is that to build really the best, most bleeding edge deep learning systems, well, certainly on my teams today, we routinely do things that are so complicated. I don't think any one human on this planet has both the deep learning knowledge and the computer systems knowledge in order to build some of the problems. And so I'm increasingly seeing teams set up org structures where their AI teams a collaboration between the machine learning, deep learning team, and the computer systems team. And I actually believe that the bleeding edge of deep learning is shifting to HPC, right? High performance computing or supercomputing, because that's what's needed in order to build really large enough computers in order to process the huge amounts of data we now have. So if if your friends, colleagues ask you, why is deep learning taking off? I tend to draw this picture. And of course, the scale of computation has also enabled a ton of algorithmic innovation, right? And the algorithmic innovation is important as well. Wrapping up the title, nuts and bolts of building AI applications using deep learning. So, with all the work going on in deep learning, I thought I'd give you a course categorization or course bucketing to give a very high-level explanation of how I think about overall priorities in deep learning, right? So there's been a lot of work in what I call, general neural networks, and what I mean by that is let's say the densely connected neural networks, right? That output whatever. So we use this for, I don't know, if you don't have a better idea for a neural network architecture, often use the densely connected neural network. There's a lot of work on neural network structures, optimization algorithms, even activation functions, details of this. And then in my mind, the other major buckets of progress have been sequence models. Right, and so this includes all the work on recurrent neural networks, on GRU, LSTMs, CTC, a whole bunch of sequence models. Right? And so this includes models for natural language processing, since language is usually a 1D sequence, models for speech recognition, it was all the time series, a lot of work on sequence models, a lot of work on image models, and so 2D/3D, right? And so mostly this would be maybe convnets and variations thereof. And I guess, and finally, there's another bucket that I'm going to call other, or maybe I'll call this, well, sometimes my friends call this future tech, but I'm going to put unsupervised learning and reinforcement learning, maybe a few other things down here, right? And a lot of work on unsupervised learning. Actually, I'm super excited about still old ideas in sparse coding, ICA, slow feature analysis, bunch of ideas, and a lot of excitement about reinforcement learning. So it turns out that if you look at what's creating the economic value today, right? If you look at what's really shipping, like what are hundreds of millions of users' lives, improving today because through deep learning, almost all of it is these three buckets up there, right? And almost all of it today is supervised learning. With some forays into transfer learning and multitask learning that I'll say a little bit more of just now. But I feel like when you look at what's really shipping in products or what's really touching a lot of people today is mostly that. When I gave a similar presentation a few months ago and I said something like this, people thought I was dismissing the other bucket, and that's totally not my intention, right? I'm actually very bullish on unsupervised learning, with some teams work on reinforcement learning as well. I think the challenge of unsupervised learning and reinforcement learning is that today we have so much labeled data that there's still so much value to be exploited, just turning the crank on supervised learning on the huge amounts of labeled data we have. And I think one of the bottlenecks on supervised learning still feels to me computational scale, right? If one unlabeled example is worth, I'm going to make up a number, if one unlabeled example is worth 1/10 as much as a labeled example, then maybe you need 10x as much data, and so you need 10x as much computation. And so it's frequently pushing up against scale. And reinforcement learning, so I worked on reinforcement learning for my PhD thesis, right? I worked with PW, Adam Coles, and I flying helicopters. There's a lot of work there. The Achilles heel of reinforcement learning is that its hunger for data is very hard to satisfy for most problems. So these supervised learning algorithms need so much data, we're already sometimes struggling to find data to feed these giant beasts. And unsupervised learning, in general, needs even vastly more data than supervised learning, which is why I think most of the application of reinforcement learning have been on playing games, because if you're playing video games, you could play infinite amounts of video games like a computer simulation. So reinforcement learning is fantastic for playing games, but outside playing games, some examples, PW team done very nice work on robotics when they have a simulator. So there are some cases where this looks promising, but the need for massive amounts of data, I feel like is still a barrier for wider adoption. But just to be clear, I'm not at all negative on these. Do work on these. I mean, today's future tech is tomorrow's mainstream tech, right? Actually, maybe as an example, when was it? I think 2008, at the NIPS conference, when NIPS was much smaller, one of my students published the first paper on neural nets trained on modern GPUs, right, on CUDA. And 2008, training neural nets on GPUs was really controversial, right? My friends in deep learning were skeptical, but back then it was future tech, and now everyone does it, right? So I think, by all means, strongly encourage people to work on these as well, right? But having said that, if it goes to ship a product, in the next 3 months, I would focus attention on the supervised learning algorithms rather than the longer-term research things. Okay. So, in addition to scale, I think the second major trend for why deep learning is taking off and really, really working well is the rise of end-to-end deep learning for complex outputs. So scale was the first trend. Maybe the number 2 biggest trend, I believe, is end-to-end deep learning for complex outputs. And this is all supervised. Right. Okay, so here's what I mean. Several years ago in machine learning, we're mostly working on like classification and regression problems, right? So you'd have a, movie review. Sorry, I can't spell today for some reason. Okay, movie review, that's X, and you try to predict, the sentiments, right? Maybe 0 or 1, or maybe some ordinal ranking. Or given an image, right? Try to predict the category. Right, so the integer from 1 to 1,000. So a lot of the machine learning problems we're seeing at NIPS that you would have seen at NIPS a few years ago, maybe 5 years ago, were supervised learning for regression and classification, where you're trying to output an integer or a real number. And one of the most exciting trends I've been seeing across deep learning is that we now have algorithms that can output much more complex stuff than just a number. So for example, I've been super excited about, actually we've been my team's doing a lot of work on speech recognition, really a lot of teams, not just mine. But you can now input an audio and have a deep learning algorithm, not just output an integer, but output the transcription of what was said, right? So you can, take the audio recording of what I'm saying in this presentation, and with modern deep learning algorithms, like the deep speech 2 system, you can directly have a neural network output text, output a transcript. Or image captioning, right? You can input an image, and instead of just labeling it, saying, oh, that's a cat, that's a dog, you can have a image input, output a caption, output a few sentences, or output a sentence describing an image. This is first done by Mao et al., but many groups working on that at the same time. Susskiver et al. Was the first to do this, I think. Machine translation, you can input an English sentence and have a neural network output a French sentence, right? Or you can input a piece of text, or maybe features of the text, and output an audio clip of someone saying that text, or text-to-speech, right? So have a machine read out text, like the WaveNet paper was a really nice piece of work doing this, right? So with the ability of deep learning algorithms to output things other than just a number, or to output a text or audio, or sometimes, or even output an entire image, this has created a lot of new use scenarios, I guess, for what deep learning can do. And the Achilles heel is that you still need, right, a lot of labeled data. Right? And so these end-to-end deep learning algorithms work well mostly when you have a very large training set, a very large labeled training set of X, comma, Y. So, given the rise of all of these algorithms, right, of these end-to-end deep learning algorithms, I want to share some observations on when you might be able to apply these end-to-end deep learning algorithms, and when it might be less advisable to apply some of these algorithms to your tasks. Okay, and so when do you want to apply an end-to-end deep learning algorithm, right? So I thought the best way to give you a sense of this is to run through a few examples, right? And, human brain, maybe like our algorithms, learns best from examples, and I'm trying to share with you patterns I'm seeing across, many dozens of machine learning projects, right, that I'm in day-to-day contact with. So let me run through a few examples so that you can start to see some of these patterns for yourself. So one example that I've already mentioned that does work well for end-to-end deep learning is speech recognition. So the traditional speech recognition architecture had a very complex pipeline, right? So, you might input the raw audio, and then, have some hand-coded features, and then like MFCCs or some other audio features, and then based on those features, you might extract phonemes. A phoneme is something hypothesized by linguists to be one of the basic units of sound. So if I say the word cat, a linguist might tell you that the word cat contains the three sounds, the k, the a, and the t, right? And the k in cat sounds the same as, I guess, the k in kick. So this is so that's what a phoneme is, the basic units of sound. Then you extract features, extract phonemes, and then finally, right, you output the transcript. So audio to features, you use some hand-coded thing. Features to phonemes used to be various complicated models, like Gaussian mixture models. I think Li Deng and Jeff Hinton did very nice work transforming one piece of this to deep learning. And so this is non-end-to-end deep learning, right, where you have the input X and many intermediate stages before you get to the transcript Y. An end-to-end deep learning approach would input the audio and have it, so this is a deep learning algorithm, directly learn to output the transcript Y. And it turns out that this works really well when you have a lot of labeled training data, right? I think our communities went through a number of wrenching changes, actually. First in computer vision, when deep learning people started to tell computer vision researchers not to bother about the hand engineered features, there was a lot of I want to say strong emotions. I've been publicly yelled at by computer vision researchers for daring to want to replace their loving, their handcrafted features of deep learning. And even for phonemes, actually remember, I've been in, several years ago, I started to say that I think phonemes are a fantasy of linguists rather than a fact of reality. So you can guess how the linguists felt about that. But what can I say? We turned out to be right, So, but if you have enough data, end-to-end deep learning for speech recognition works well, right? But I want to show you an example of when end-to-end deep learning does not work well, right? I feel like sometimes there's a temptation to just learn everything, and it just doesn't, and it's just not the best way to build all the applications. So here's one example. All right, one of the applications of computer vision I've been excited in is like a door that recognizes your face, right? So, I guess a lot of companies have these turnstiles. So the turnstile is like a thing at the entrance, where there's a gate, right? And then you kind of, I don't know, boy, and then you're here, right? And you walk up to the gate, and this gate kind of swings open. You know what I mean, right? Like the turnstiles you go through into movie theaters. All right, cool. So a lot of companies, including Baidu, right, we have to carry a badge, like an RFID badge, to swipe the badge, so it lets us into our office. So we want to build a computer vision system, so you put a camera here, and it just recognizes your face. And so now in headquarters, I don't need to carry my badge to go to the entrance. Just walk up, and then it recognizes me. It says, "Welcome, Andrew," and I just walk through. Right? It's actually pretty magical when you just walk through and it recognizes you, and you just go through. So how do you build a face recognition system in order to do this? Right? If you look at the picture of the face that this camera sees, the picture, it might see you, right, approaching from a distance, right? So this is a picture, I guess, and maybe there's like a tree in the background or something. Sorry, yeah, I don't know, and maybe that's something, right? So this is what the camera sees. My drawing's not that good. So an end-to-end deep learning system would say, well, this is X, and this is the identity. Y. So why don't we just have a neural network learn this, right? And this is not how we actually built this face recognition door system. Instead, what works much better, and there's a concrete reason for this beyond the obvious, right, is if we first run a face detection algorithm, to figure out, oh, this is a person that's about to approach my entryway. And then we zoom into where your face is, and then you have just a closely cropped face image that you then use, right, to learn to recognize your identity if you're trying to walk inside the office. Okay? And in fact, technically, just a little bit more detail, technically what we do isn't exactly this. What we actually do is learn a neural network that takes as input 2 images. So this is the reference image, right, from your employee database or something. And what the neural network does is actually takes as input 2 images, and it tells you if these are the same person. Okay? So that's how we do face recognition. We're confident enough in our system that this runs. So if someone looks exactly like me or something, that you could actually access our office if you can defeat our face recognition system, right? And so why is it that we build a system this way? Is because we don't have a lot of data when X, Y is defined on top, right? We just don't have a lot of data of people walking to the gate. But if this is X and this is Y, if X is a pair of images and Y is this is the same person or not, then we do have a lot of data, right? And in fact, the way we get lots of data, if you need closely cropped pictures of faces, there are tons of closely cropped pictures of basically headshots on the internet with a lot of sources of data like this, right? And so right now we train this system on 200 million images. right? And I just don't know where to get 200 million images of people, approaching the doorway of Baidu headquarters. We just don't have that many visitors, right? And so one of the factors that really drives decision making and whether or not to apply these end-to-end deep learning algorithms is just where can you get your label data. Oh, and the word end-to-end, it refers to the two endpoints. One end is X, the other end is Y, right? The input endpoint and the output endpoint. And end-to-end deep learning, the motivation of the term says, instead of having all these intermediate stages like features and phonemes and whatever, just look at one end of the input end, the X, the output end, the Y, and just learn a function going from X to Y. Okay, but it definitely does not work for everything. Just a couple other quick examples, and then I'll move on. I've been spending a lot of time working on deep learning or machine learning for healthcare, right? So one of the problems my friends at Stanford were looking at is, let's see. So it turns out that doctors, pediatricians, care about looking at the X-ray of a child's hand in order to estimate the age of a child, right? So given let's see. So let's see X-ray a child's hand, right? And again, and these are the. All right, that's the X-ray of a child's hand. You want to look at an X-ray like this and estimate the age of the child, right? And when I first learned about this, I was picturing, CSI applications where you find all these, children of unknown age, you need to age them. Turns out that the application isn't that exciting, is that this is a good way to screen for developmental disorders, if a child is growing faster or less fast compared to their cohort, right? So this is something that's useful to pediatricians. So so one way to do this is to first have an image, and then segment out or recognize the bones, right? Detect where the segments of the individual bones and measure the bone length, and then use that to estimate the age of the child. And so this step can be with deep learning, some computer vision deep learning thing, and this step can be with a formula, with a set of simple formulas that tell you, children of this age on average have bone lengths of like this, right? And this actually works much better than an end-to-end deep learning approach. And the reason is end-to-end deep learning, we just don't have enough data. We just don't have enough images. And the problem of going from images to recognizing the bones in an X-ray image is relatively simple. So with a smallish amount of label data, you could do this. But doing this, is just, we just don't seem to have enough data to do that, right? Couple other examples, take autonomous driving. Right? A lot of teams now have evolved to a standard architecture for autonomous driving, where you look at the image or the radar or the LiDAR or whatever in front of you, the sensor data, and then you check where are the other cars, where are the other pedestrians, or where are the pedestrians, and then based on that, you plan a route, decide, well, how am I going to steer around all these obstacles, and then, you have a controller, right? To output the steering. So going from image to these detections is usually deep learning. The way you plan a route can be a traditional planning algorithm with maybe a little bit of machine learning tossed in to fiddle the cost function, but basically traditional planner and then a traditional really, classical control algorithm to output steering. And this I would say that, the world's most effective self-driving cars today, I think pretty much all uses architecture, right? You can also try end-to-end deep learning. Input an image and train a neural net to try to output the steering directly. Dean Pomerleau at CMU did this like 20 years ago. NVIDIA is doing this. There's a guy called George Holtz who's been doing this. And this is enough to do some very cool demos. And maybe this will work in the future, but I find this very difficult to get to work right now because it's just difficult to get enough XY data to drive this to the 99.999 or whatever level accuracy is needed in order to make sure your self-driving car is safe. Okay, so I think that there's a lot of deep learning. May I just give you one last example, and then I'll finish. There's a lot of scenarios where it's tempting to apply end-to-end deep learning, right? But unless you have enough data and it fits in the right context in your bigger architecture, it doesn't actually make sense. I'll just mention one last example. you know, a lot of people work on chatbots, right, or conversational agents. Like there's a Facebook app bot store, Microsoft's work on it, Baidu have our own conversational agent. So how do you build a conversational agent? One way is to see what your user says and then have an RNN try to output a response. This is end-to-end deep learning. And it turns out that you could do this well enough to write a research paper and have cherry-picked examples that look cool. But today, this approach doesn't work well for anything but the most rudimentary, kind of semi-entertaining, but not really chatbots. And instead, the best systems all have text and then some inference engine, right? And then have something else for the response. And there are deep learning components in here, but it's not just end-to-end, right? So this is so I think that one of the challenges of applying deep learning is that even though we can input stuff and output stuff, that there's very rich inputs and very rich outputs, one of the factors that affects whether or not you succeed is to figure out where are the endpoints. How do you define X and Y so that you have enough data for X and Y in order to learn a function of the complexity needed in order for your overall system to work. And just to go back to this example, the reason we chose this architecture was because for this deep learning problem, right, input a pair of images and just tell you if they're the same person. We have 200 million images, so we chose those as the X and Y endpoints. And for a lot of the examples where I said end-to-end deep learning doesn't work, the main challenge is when you don't have enough data for both endpoints. Okay? How am I doing on time? Okay. So with the rise of end-to-end deep learning, all of these applications we can build, one additional shift that I'm seeing is, I want to say, is how we strategize and how we prioritize in a machine learning project. All right. So something that happens all the time, right, is you might build a machine learning system, and then you try it out, and it doesn't work as well as you're hoping, right? It happens to us all the time. And when you're in that situation, you or the team you lead or the team you influence will have a lot of actions for what to do. So if you build a face recognition system that doesn't work as well as you hoped, what do you want to do? You could collect more data, right? You could train longer. You could try a different neural network architecture. There's a huge space of neural network architectures to explore. You could try regularization. You could try a bigger network. Maybe throw some GPUs at it. You have a lot of actions. You have a lot of options for what to pursue. And it takes quite a bit of skill to make these decisions. And if you pick wrong, you can literally waste months of work, right? Which as I just discovered last night, one of the teams whose work I'm aware of just did, right? And so I want to help you avoid that situation. So in this next section, what I want to do is present to you some of the maybe best practices I'm seeing that will help you drive effective decision making for your own work or for your organization's work. And a lot of this is very practical. This is about really simple analysis of problems that will tell you what are some promising ways forward and what are some non-promising ways forward. And just a warning, when I present these things, usually people nod their head and go, oh yeah, that's pretty obvious. But the challenge is not looking at this and kind of agreeing that the principles are described as sound. The much harder challenge I tend to find is when next Monday you go back to your office, taking these high-level principles to talk about and mapping them to whatever you need to do at your work next week, right? So, all right, I'm going to keep using speech recognition as a motivating example. Let's say your goal is build a human-level speech recognition system. Okay, so your goal is to build a system that can recognize speech as well as a typical human can, right? So common practice is if you have a training set to split it into train tests, maybe 70% train, 30% test, or maybe I'm going to say right? Or maybe 60% training, 20% development, 20% test or something, right? Or maybe 70-30 or something. So the training set is the part of your data you run through your neural network. The dev set is the part of the data that your team will, look at all the time in order to tune parameters and all kind of whole dot cross validation set. And the test set is the final test that you use to evaluate performance, right? So you want spatial data like this. And one of the most common diagnostics to use is to plot the following three quantities. And when I say this, it sounds so simple, right? It sounds, frankly, just some of you say, gee, this is so obvious. Why is Andrew talking about this? But I find this done surprisingly not often enough in a lot of teams, right? But there are three numbers that are very useful to plot. One is to figure out what is a human level error. And let's say that on this data set, humans make 1% error, right? And then also measure your training set error, which is for the data that you trained on, how well do you do? And let's say you get a 5% error on that. And then also plot your depth, and then also just measure your depth set error. And let's say for this example, it's 6%, okay? So looking at these three numbers, so some of you, this is a standard bias variance story, right? With some differences, and we'll make this more complicated in a second. But if you have a problem like this, then this gap between 1% and 5% error tells you that you're not even doing that well in your training set, so you have no hope of matching human level performance on the test set if you aren't even matching human level performance on a training set. So call this the bias, or maybe the avoidable bias. And I'm going to use the terms bias and variance in a way that's slightly different than how the statisticians define it, but I find that the way I use these terms is more useful for driving machine learning progress than necessarily the way it's always defined in the formal literature, okay? And here, the difference in training set error and depth set error, this I'm going to call, right, the variance. So just how well are you generalizing from data you've trained on to data that you've not trained on. And let's see. And if your numbers look like this tells you that you're not even fitting the training set that well, and you should probably focus your actions on first fitting the training set better before you go on to worry about other things, right? So some other examples, so kind of using this row of numbers, if you saw numbers that look like this, 1% error for humans, 2% error for your training set, and 6% error for your dev set, then this means you've overfit the data, right? Because you're doing pretty well in the training set, nearly human level performance, but it's not generalizing, so maybe it's overfitting. And if it looks like this, 1%, let's say 6%, 10%, then this is where you have high bias and high variance, right? Where you're not doing well on the training set and you're doing much worse on your dev set compared to your training set. So this leads to so based on this simple analysis, this leads to maybe almost a recipe for driving machine learning progress, right? And I've been surprised, and again, this is one of those things that's so simple, but a lot of teams don't actually do this. And I find that when teams follow this recipe, as simple as it is, a lot of teams make a lot of progress on the applications, right? But here's a simple recipe, which is, let's ask if your training error is high. Right? If it is, then you have a bias problem. So, try training a bigger neural network, or train longer, or run gradient descent longer, or try a different optimization algorithm. Or you could also try a new model architecture, like a new neural network architecture. Okay, but basically these are ways to help fix, say, bias problem. Right? And then once you're doing well Oh, and then after doing this, you kind of come back, right? And then once you're doing well on the training set, see if your def set error is high, right? And if you're doing well on the training set but not on the def set, that means you have a variance problem. So try to get more data, maybe try regularization, or try a new neural network architecture. And the new model architecture, that's like the Hail Mary, I guess. But with a new model architecture, hopefully you can make anything work, right? But so this is trying to address a variance problem. And I guess, if you're doing well on the dev set, you just make sure you're doing well on the test set. I'll expand this out a little bit later. But if you're doing well on the dev set, hopefully you're done. So one of the differences I'm seeing between these sorts of bias variance analysis now, kind of in the deep learning era, compared to earlier generations of learning algorithms, is that even though we talk about bias and variance, I find that we talk about the bias variance trade-off less than we used to, right? And I think it's because when we're training, older generations of learning algorithms, we could try things like regularize, right? And regularization, it tends to decrease variance but increase bias. And we had relatively few ways to squash bias without hurting variance or squash variance without hurting bias. I think one of the reasons that deep learning has been taking off is because with deep learning, we have somewhat magically a way to reduce bias without increasing variance or reduce variance without really hurting bias. And is really, bigger model and more data, right? These are sort of almost magical ways to reduce bias or reduce variance without really much hurting the other one. And so long as you can always keep on doing this, which is challenging, but so long as you have the compute budget to keep building bigger models, and so long as you have the ability to go out and acquire more data, you could almost always keep making progress on a machine learning problem. Although, of course, there are practical limits to how big you can make them or how much data you can acquire as well. But I think that this formula, this crank, means that so long as you can keep doing these operations in the green boxes, you could usually keep making progress on driving performance of on the problem. So, let me see how I'm doing on time. Okay. I'm going to fill out a more complicated version of this as well, right? One of the, driven by our algorithms' huge hunger for data, one of the things I'm seeing a lot, and I feel like this will come up in your team eventually, right? If you're working on an application, there's a very high chance that someone will eventually mention the idea of automatic data synthesis. Right. But I think because of the huge hunger for data of our various algorithms, I'm seeing very innovative work, ranging from crowdsourcing to data synthesis to other things for organizing the data of an enterprise so that you can turn this crank as far as possible to drive progress. I'll just mention one of the techniques that sometimes works very well and sometimes is completely useless is automatic data synthesis. And here's what I mean. So, synthesis. Right? If you're working on OCR, optical character recognition, one way to get an infinitely large training set is to, suck random images off the internet. So, I don't know, let's say take a holiday picture, whatever, right? Me and my wife on holiday, right? And then take a random word and fire up Microsoft Word and select a random font. I'm going to say machine learning, and just print the word, that was the word machine on a random background in a random font. And we've just synthesized a piece of data, an image, on which OCR is supposed to output the word machine, right? And so by taking random backgrounds and random fonts and random pieces of text, you can synthesize almost infinite amounts of training data. So when actually my Stanford students were working on OCR many years ago, this worked really well. But one trend that you see is that in order for this to work well, I find that in practice, you need to do a lot of finicky work to fiddle with the distribution of the data. And when we're doing OCR, one thing that, to our surprise, really worked, made a huge difference was just kind of color balancing the synthesized data, So the distribution of colors was similar to that of our development and test sets data. Right? And so often there are little tricks like this. So what I often see is that if this is time, right, and this is maybe payoff, a lot of times I see people work on synthesis kind of get no payoff until eventually they figure out some tricks, and then it works really well. So I've seen that happen on multiple teams doing automatic data synthesis. And maybe it's kind of unfortunate. We've gone from hand engineering features to hand engineering data sets, but maybe this is I don't know, maybe this is just a different way to express some prior knowledge. Another example, speech recognition. Right? One thing that does work very well is to take clean audio. So take audio of your voice, my voice, someone saying words clearly, and just add background noise, right? So because of the superposition property of sound, basically sound waves add. If you record what the inside of a car sounds like, and you record me speaking, and you add those two waveforms, you end up with an audio clip of it sounding like me talking in a car. Right? And so with this, you can synthesize voices against a lot of different background noises and create huge data sets. And similar examples in NLP and so on. So actually, for grammar correction, we're taking English sentences and adding random grammars to see if a random grammatical effects, random grammatical errors to see if a neural network can input an ungrammatical sentence and correct it. Right? So you can synthesize a lot of data like that as well. So the thing to watch out for is the following. Sometimes, let's take noise synthesis, right? In the very early attempts for noise synthesis, I saw some of our teams take, let's say, 10,000 hours of clean audio data and 10 hours of noise, right? And when you synthesize this together, to the human ear, this sounds perfectly fine, right? So 10,000 hours of speech, and say 10 hours of what the inside of a car, what the cafe sounds like. And then you just, take this different 10,000 hours and add it to different random subsets of your background noise. And to the human ear, this sounds perfectly fine. But what you find is that there's a good chance, there's a very real risk that your neural network will overfit to this 10,000 hours of noise. And you can't tell because to your ear, the inside of one car sounds just like the inside of another car. One cafe sounds just like another cafe. So what works much better is if you have 10,000 hours of speech and, maybe at least 100 hours or 1,000 hours of background noise, so you're less likely to overfit to this cafe as recorded at 7:30 p.m. that day. Right? One other example of this is an idea that's come up over and over. So many teams have independently proposed this idea, which is, let's say you want to do computer vision to recognize cars, right? So where can you get a huge data set of cars? Boy, is this how you draw a car? Hey, not bad. All right, cool. So where can you get a huge data set of pictures of cars? Well, so many people have independently come to the idea of looking to computer games, right? Video games. Let's see, Grand Theft Auto, right? A bunch of cars in it. So why don't you just use Grand Theft Auto and use the computer graphics they've already worked so hard on to get you a bunch of pictures of cars? This is one of those ideas that I think works better in theory than practice. And the reason is, if you look at a video game, the entire video game might have, 20 different models of cars in the entire game. And that's plenty of models of cars. If you play a video game, there are 20 cars you don't notice, right? This feels like 20 cars, looks like a very rich world. But the reality is the world has way more than 20 models of cars, and your algorithm will overfit to those 20 models of cars. So to draw a picture, if this circle is a space of all possible cars, there's a lot of possible cars in this world, it's possible that you're synthesizing only a tiny subset of the space of all possible cars, and to the human eye, it looks fine, right? You really can't tell, but the learning algorithm will rapidly overfit to this, okay? And by the way, for those of you that know about GANs, right, really Ian Goodfellow's work, I feel like some very interesting analogies there to using a learning algorithm to discriminate, kind of synthesize data from real data, but anyway, that might be more of a research issue, right? Other best practices that I've learned, one is unify your data, I've seen this happen. I've seen this in multiple companies. I'll just speak to Baidu, but I've seen this in a lot of large tech companies. One of the things that drive your machine learning progress tremendously is you build a unified data warehouse so that all your user data comes into one place, right? Many large tech companies have done this by now, but if you haven't yet, consider doing so. Because what I see is that if your developers need to run around and talk to 20 different people in order to get access to data, it's just going to dramatically slow down their progress. So at Baidu, I own Baidu's user data warehouse. So when a user touches almost any property on Baidu, their data comes to a database I'm responsible for. And the ability to bring together data makes it much more efficient for machine learning researchers and engineers to develop on top of that data. And I think if you're having trouble getting this done within your corporation, the practice I recommend is that data access is up for discussion. So talk to teams in your company, right? Data access policies can be debated because we do need access controls and privacy and auditing and make sure this secure and so on. So the database access policy can be discussed, but whether or not the data should come into a central data warehouse, that should not be up for discussion. And if you can bring your data together in your corporation, you'll be able to drive much faster machine learning progress. And maybe to make an analogy, I think data is like dynamite, right? Stick of dynamite. I don't know. You need to put a lot of it together to make a big bang. And if your data is scattered in tons of disjoint data sets all over the place, it's just much harder for you to have as big a bang. Okay. All right. So I think the ability of the recipe I drew on the left to drive machine learning progress means that we have a huge hunger for data. And so these are maybe some of the practices I'm seeing, as well as crowdsourcing, in order to drive more and more data. Oh, and today, I sometimes launch products where our main motivation is data acquisition rather than even revenue, for example. Right? But I want to flesh out the picture on the left some more. Right? So there's another practice that we learned that we learned in machine learning that doesn't apply when you're in a lot of problems when you're trying to ship a product, when you're trying to build an application. Which is this idea that your training and your test sets come from the same distribution. I think that when your training and test sets comes from the same distribution, the theory is much nicer, you can prove much nicer theorems, and it's just much easier to work on problems when your training and test data come from the same distributions. But over and over, especially in this era where algorithms are so hungry for data, it's just so often not true that your training distribution and your test set comes from the same distribution. So let's motivate this with an example. Let's say that you are launching a new product that's a speech-enabled rear view mirror, right? So this is a real product. A bunch of companies sell this. We have our version, but a whole bunch of companies sell this, mainly in China, I think. Not sure, less so in the US, not sure about Europe. But some of us have cars with like a speech-enabled dashboard or a speech-enabled navigation system, but that turns out to be hard to retrofit, right? But we found that if you've already bought a car, it's quite easy to rip out your rear view mirror and put in a near rear view mirror with electronics and a microphone and a SIM card so you can access the internet. So a speech-enabled rear view mirror actually works quite well. You can say, hey, rear view mirror, please find me directions to the nearest Starbucks. Okay, so this is actually a real product. So how do you build a speech recognition system for this, right? You might have 50,000 hours of general speech data. So right? Been working on speech recognition for a long time, so you might have a lot of data from collected off crowdsourcing, collected off mobile apps, collected a lot of places that is not data recorded from a rear view mirror in a car, right? And as you start working on this product, maybe you go and collect additional 10 hours of in-car rear view mirror data. Okay, so go ahead, snap a rear view mirror in the car, drive the car around, have someone talk to the rear view mirror while you're driving with all the background noise in the car, and maybe you can collect 10 hours of data for that. So the question is, how do you define training, development, and test sets for this problem, right? So your training set is different in distribution than your test set, right? So, well, here's one way to do this. You could, well, you have a lot of data here, so let's train a neural network there. And then let's carve off some subset of the speech data to be our development data. And then in the end, we care about this task. So let's set that as a test set. Okay? So a lot of teams will do this. In fact, I know a team that did this. Not at Baidu. Right? Turns out this is a bad idea. And here's why. When your development set and your test set are not drawn from the same distribution, what will happen a lot is you have a team, this is how a machine learning team operates, right? You have a lot of ideas, you try hyperparameter, try new model architecture, and you run it through your training set and see whether it works on your development set. And if it does better on your development set, you keep the idea, and if it works worse, you toss the idea. And machine learning teams iterate quickly, trying a lot of ideas and evaluating them on the development set to see what works. And so if you set up your train, dev, and test sets this way, there's a very good chance that your team will spend weeks or months until you're doing well on the development set. And then when you suddenly try it out on the test set data, you find that, gee, all this work we did doesn't generalize to the distribution we actually care about. I know this sounds simple, but it's very surprising how many teams use development and test sets that are drawn from different distributions, right? This sounds simple, but this is one of those ideas that has a huge impact on teams' productivity. And I've seen a lot of machine learning projects, right? So a much better way to do this is to let this be your training set, and then take the 10 hours of data you have, right, and make part of this the development set, and make part of this the test set. And in fact, there's one other tweak to this, which is sometimes I will also take the training set and carve off just a small subset of it, and I'm going to call this the train dash dev set, okay? And maybe what I'm going to present to you is a way of analyzing your data that I think will help point you or your team in a clearer direction of progress than other things you might try. Right, but take your training set, carve off just a small subset, maybe 20 hours of data. I'm going to call this a train dash dev set, and then you have a development test set. So first, one important thing to notice is that the development and test sets are drawn from the same distribution. Okay? And this is one of those practices that will make a huge difference in the performance of your team. I find it hard to emphasize that enough, right? Because the way machine learning team operates is the team will very rapidly make progress on the dev set, and so you want your dev set and your test set to be whatever you ultimately care about, right? So as much as possible, and you don't need a lot of dev and test data. This is just for the purpose of evaluating your algorithm. So usually quite a small set, but enough to evaluate the performance of algorithms is enough. But I would try really hard to make sure your dev and test set data correspond to whatever data you actually want your algorithm to do well on, which in this case means going out and collecting just enough in-car rearview mirror speech data to make sure that when you actually do well on this, that it actually helps your product. And then, so the training set, this is what will feed to the neural net. Right, and then your little, I'm going to call that the train dash dev set. And so this is the analysis we can now do. Let's say human level performance is 1%. The training set performance is, I'm going to use very, coarse numbers just to make the examples easy, right? Let's say human level error is 1%, and you have 10% error on your training set. let's say your training dev error is 10%, your dev error is 10%, and your test set error is also 10%. Okay, this is a very simple example, just to explain the concept. What this means is that, so the gap between human level and training, this is really your bias, right, or your avoidable bias. Right? You're not even fitting the training set, so how could you possibly hope to be at human level performance? The gap between training and training dev, this is your variance. Right? So the training data and the training dev are drawn from the same distribution. So this shows that the gap between this second number and this third number is the difference between how well you do on data you trained on versus data you didn't train on when they come from the same distribution. Right? This gap is the amount to which you have a data mismatch issue. Right? In which you now go from trained dev, which you've not seen before, to dev, which you've also not trained on before. It's just from a different distribution. And so that gap accounts for how much, the fact that you're testing on a different distribution than training, how much that hurts you. And then this final thing is how much you've overfit dev set. Okay? So just to, let's see. So just to give one more example, right? If your numbers look like this, 1%, 1%, 2%, 10%, right? 11%. If your analysis comes out this way, then you see that the huge gap is here between your training dev error and your dev error. And this means that most of your error is from data mismatch, right? You're doing great on the data you're training on, but not so well on data, on this new distribution of data. And this suggests some things to try and some things not to try, okay? So, I don't know. I'll be honest, sometimes when I present this material, I get criticism that, like, hey, Andrew, how come there isn't more math in this? Like, where are all the equations? But I'll be honest, when I look at what holds up the performance of machine learning teams, many machine learning teams trying to ship product, trying to make progress on concrete applications, this, frankly, is the bottleneck quite often, much more often than that, they couldn't do some piece of math or have some complicated algorithm. And I feel that in the NIPS community, with all the great work that we do, there is still a gap between the problems we study and publish papers on and the practices that are most effective for driving performance on concrete applications. So I would say that I've seen this particular practice actually help quite a few teams accelerate their progress as well. Right? So, all right, I'm going to come back to this and flesh out this formula in this era of mismatched train test data. And so first two parts stays the same as before, except that now, instead of dev error, this is train dev, right? And so first make sure you're doing well on the training data, then make sure you're also doing well on the train dev error. So make sure you can at least generalize the data from the same distribution as what you're training on. And if not, then get more data and do this formula. And after that, once you're doing well on train dev, I would check, is your dev set error high? Right? And if it is, then that means you have a data mismatch problem, right? And so I would try to make the data more similar. Maybe play with data synthesis. Right? For example, if all your training data, for the rearview mirror example, if all your training data was against a clean background, and you found that all the data from inside of a car has a lot of car noise, right? The car background noise, you could synthesize the car background noise against your clean training set and synthesize data that sounds more like your dev set and your test set. There is an academic literature on domain adaptation. It's an important research problem, but I'm putting this in parentheses because I don't see those algorithms used that much still today, right? I think because the algorithms I'm seeing tend to be relatively specialized. So it's used a little bit, but not as widespread as one might hope. And then finally, try a new model architecture, right? That's always a solution. And so I'm going to say this solves the data mismatch problem. And then once you're doing well on the depth set, I would just, right? See how your test set error is, and if his test set error is is not high, then you're done, right? And if your test set error is high, then I would get more dev data. Right, and I guess if you end up with a high test set error but a low dev set error, that really means you've overfit the dev set. Right, did too much parameter tuning on your dev set. So go back and get a fresh dev set, or at least get more dev set data. Okay. So I feel like what I'm seeing over time is that machine learning should be less and less a seat of the pants gut feeling type of ways of making progress, right? I think that, I want to make an analogy to software engineering, right? Many decades ago, we started to, have computers and the programming languages, and over time, we had to learn how to organize the act of computer programming. We came up with these things called function calls and then objects, and we learned how to do object-oriented programming. We learned how to, what is a RESTful API. But we found all these ways of more systematically organizing the work of computer programming. And in the history of computer science is really, first there came all these cool ideas of, well, you can program a computer, and then we learned how to organize the work. So today we have pretty systematic ways. If you need me to write a mobile app, I kind of know how to do that in a systematic way. I feel that machine learning is making very rapid progress, but just like computer programming maybe 30 years ago, there are a lot of seat of the pants, gut feeling decisions, like, hey, let's have a lot of go-to statements. Well, we don't do that now because you learn how to organize the work of computer programming. And I feel that what I'm trying to present to you, and what really I hope all of you can contribute to the literature on, is with all of these new tools of machine learning, how can we organize the work of machine learning so it becomes more of a systematic process that drives predictable results rather than a seat of the pants, well, I have 10 years of experience, so I'm going to go by my gut feeling for what we're going to do type of activity, right? And I feel this process, I know it's not sexy, right? It's like this thing you do, but I actually believe, I've actually seen teams following this process able to much more systematically drive progress on concrete machine learning applications than kind of more seat of the pants or gut feeling based decision making. Right? One more comment, one thing I still see today is if you really understand bias and variance, you can make a lot of progress on machine learning, right? And I know maybe many of you learned about the concepts of bias and variance a long time ago, but the concepts of bias and variance is pretty much deeper. And all this is just about bias and variance. And the consequence of all this is, machine learning algorithms today are very good at one thing. They're good at multiple things, but there's one thing they're really good at, which is if you have a lot of labeled data from some distribution, it's pretty good at learning to generalize to data drawn from the same distribution, right? With a big enough neural network, you could do that. So that's one thing learning algorithms can do very reliably. And there are other things it can do as well. And a lot of this process is about how to exploit that observation I just said. If you train on a distribution with enough data and a big enough neural network, you can probably generalize to more data drawn from a similar distribution. And a lot of these are, with that implication, how can you use that to drive progress in a systematic way? Okay? I just want to give, and so this type of analysis where we measure these 5 things will often clarify decision making for what to do and what not to do. Just want to mention real quick, kind of a advanced version of this. right? So why did we choose to measure these 5 things? I'm going to just very quickly tell you the full framework of analysis, but you very rarely need, usually what I just wrote just now will be good enough for you, but I'll just tell you the more general picture I tend to think about in my mind, which is there are 3 things you could ask, which is one is human level performance, how well do humans do? One is performance on examples you've seen. And error on unseen examples. So this is performance on examples that your algorithm has trained on, performance on algorithm, examples your algorithm has not trained on, and then here I'm going to put the general speech data. So 50,000 hours, and here is the in-car data, right? Let's say 10 hours. And so what we've seen is, for the things we're measuring, we measure human level performance. We measure the training error, the training dev error, and then the dev/test error. Right? And you've kind of seen the dev set a bit, but I'll just leave that together for now. And so what we've been measuring is the difference between these 2 and these 2 and these 2, where the gap between this is the bias, gap between this is the variance, gap between this is the data mismatch. Sometimes I ask my teams to figure out this number and this number as well, and sometimes that helps drive additional insight. But I guess for the projects I've worked on, it's been maybe a minority of projects where we wanted to do this level of analysis and kind of fill out this huge matrix. But really, the vertical axes are the different distributions of data you have, right? In fact, if you have 3 different distributions of data, maybe you have a partner provide you data, right? You can also fill out these things for the different data sets you have. And I find that filling out this matrix often drives a lot of insight into what is working, what isn't working. But the most common one is just a subset of this that I drew just now. Okay? Usually you don't need this level of complexity. All right. So, so one of the things I hope you will do is when you go back to your company or your office or your university or your institution, for a problem where you're trying to make progress, make sure the development set, the data set you're doing the day-to-day optimization on, that's drawn from the same distribution as your test set. And I think one of the reasons that's become more and more important is that machine learning, well, this is how I work on a problem, right? I'll often have an idea, like, hey, let's build a face recognition system for the door entryway, right? So you can walk in with just face recognition. And then you have to code up your idea, and then you have to run an experiment, right? And evaluate how well your idea for a model architectural data set or whatever works. And based on how well that worked, you then have new ideas for how to change your architecture or add more data or try regularization or whatever. And I feel like that machine learning today has become very iterative, frankly, more than it was 10 years ago. And here's why. When we're training support vector machines was relatively turnkey, right? Frankly, it was either a linear kernel or a Gaussian kernel. You just run it, it works, or it doesn't work. And if it doesn't work, you fiddle the features or something. But there wasn't as much to fiddle around and try. Whereas today in deep learning, maybe because deep learning is still a little bit immature, I find that there's just a lot more hyperparameters, a lot more model architecture choices, a lot more choices for data sets. And let's see. I think I wrote my first neural nets paper in like 1993, something like that. It was a really bad paper. Don't read it. But despite having worked on neural nets for, I don't know, boy, what year is it today? Anyway, for many years, right? 20 plus years. I feel like I don't know, when you give me new applications, I don't know what neural network architecture will work best. I don't think anyone. It's very difficult, even for those of us that worked on this for some time, to just get it right the first time, because there's a huge space of model architectures, and the way that and in order to get the good progress, we really have to try a lot of things. Maybe if the theory of deep learning matures, we can try fewer things, but today, your ability to rapidly try many ideas and accept some and reject some, that is just part of the formula for making progress, right? There's a lot of creativity in the model architectures and what to try, but I don't think I've ever gotten the model architecture right on the first time, right? It's like never. So I feel like machine learning has become more iterative today because there's just more hyperparameters we need to fiddle with now compared to 10 years ago. And this is why having a dev and test set as well as a metric is very important, because you or your team will make faster progress. You can quickly try an idea, get a number to say, oh, accuracy went up or accuracy went down, and just keep on optimizing that number in order to drive performance, right? I'll just mention one counterexample to having training and test set errors drawn from the same distribution. There's one very difficult scenario where people don't do that, and this is a scenario. Let's say you want to build a self-driving car, and you want your self-driving car to work everywhere in Europe, right? Because we're in Barcelona, so let's use Europe as an example. And so you might send your self-driving car to collect a bunch of data from Barcelona, right? And then go send it to London and collect a bunch of data there. And then go send it to Munich and collect a bunch of data there. And go send it to Paris and collect, maybe 1,000 hours of driving data, right, from each of these cities. Right? And after having trained it on these things, you now want it to work everywhere in Europe. Like maybe you want to work in Milan, I don't know. And the problem with this is that it's not clear how to define your dev and test sets, right? One way to do so is to take 500 hours of each of these, so you have 4 cities, right? Barcelona, London, Munich, Paris. You could take this data and take half the data from each city, or some data from each city as a dev set, some data from each city as a test set. That would respect this rule of making sure your dev and test sets come from the same distribution. But what it doesn't do is you probably overfit to these 4 cities. So when you go drive in a new city like Milan, who knows how we're going to do. So this is maybe not a great option. Another option would be to take some data from these cities as dev and maybe take that as test. So this breaks the rule of having dev and test from the same distribution. The reason we're stuck in this is because when you're collecting data with a self-driving car, you can't collect data sampled uniformly at random from Europe, right? The way you collect data is you send a car to a city, you collect all data in that city. So the way you collect data is highly correlated. And this creates a problem because even though we have 4,000 hours of data, you're really trying to do machine learning with 4 data points, right? You have seen 4 cities and you're trying to generalize to a 5th city. So this is really machine learning with 4 examples. This is not the regime of big data. And similar to, the early example where I gave, if you do computer vision with 20 examples, you have to rely on hand engineering. If you're really in this setting, hand engineering will count much more because I don't know how to train on 4 cities and generalize to the 5th city, right? A lot of that will be hand designing things rather than having an algorithm learn from data. So this is a tough situation where because your data is very non-IID, it's more difficult to follow the guideline that I gave just now. For this particular example, I would probably use this as a dev and use a different city as a test because this is a harder problem. So we can measure how well it generalizes to a new city, but this is just not a great problem because it's like saying, well, you have 4 data points. How do you do machine learning? There isn't a great answer to that. I think in practice, if you want your car to operate in Milan, go and collect data in Milan, right? Which I hear is a fun city. All right. So, there's one other theme I want to touch on. One of the things I've mentioned many times today is comparing to human level performance, right? So, it feels like in the last few years, we've seen a lot more research papers comparing machine learning algorithms to human level performance. I think the two reasons to that, one is, our algorithms are finally working much better, that it's reasonable to compare them to humans, as opposed to, wow, humans are amazing and the machines just can't do it, right? So our algorithms are doing much better, so we can compare them to human level performance. But there's a second reason that I think is germane to how you drive your machine learning project's progress. On a lot of projects, if the horizontal axis is time, right, and if the vertical axis is accuracy, if humans can achieve a certain level of performance, one thing you often see, this is an empirical thing I've observed in a lot of projects, is that you tend to make rapid progress until you approach human level performance. And then as you approach and as you surpass human level performance, progress often slows down, right? So this is just a pattern I've seen in a lot of projects. I think there are two reasons for this. One is that humans are pretty good at a lot of the tasks we apply deep learning to, right? Things like perceptual tasks, like image recognition, speech recognition, natural language processing. Humans are actually pretty good at a lot of stuff. So human level performance is quite close. In fact, it's a reasonable proxy for the Bayes optimal error. Right? So the Bayes error or the Bayes rate is the mathematically optimal error anyone could possibly get with the best possible function mapping from x to y. Right? So Bayes optimal error, which are sometimes called Bayes error, is just the best error rate anyone could possibly hope to get on this problem. And so human level performance is a pretty good proxy for Bayes error. So one of the reasons progress slows down is by the time you hit human level performance, you might be quite close to the mathematically best possible error rate, so there just isn't that much more progress to make. But there's a second reason why human level performance, you could drive progress faster before you approach human level performance. One is that you can get data from humans. Right? So long as humans outperform your algorithm on image recognition or speech recognition NLP, you can ask humans to label data for you, so you have a good source of data. And you can also use human insight from error analysis. Right? So when a human gets an example right and your algorithm gets an example wrong, you can ask a human, hey, how did you figure out that was that? Right? So actually, speech recognition, if I say, please navigate me to the Moscone Center. I don't know if you know what Moscone Center is. It's a place in San Francisco, right near where I live. The only way to know how to spell Moscone is you have that in your address book, basically. So with that insight, you can drive performance. And then finally, to the extent that human level performance is a proxy for Bayes error rate, it helps you to estimate bias and variance. So let me illustrate that with an example. Right? Let's say that on an image recognition task, your training error is 8%, and your dev error is 10%, right? What should you do? Okay, and I don't know. But if we know that human level error were 1%, then I know that Bayes error is 1% or lower. Right? Humans can't outperform Bayes error. So I know that I should first try to do much better on the training set. Right? But if in contrast, if human level error was 7.5%, then we're doing pretty well on the training set, and so maybe I should focus on the variance. Right? And so the ability to use human level error as a proxy really for Bayes error tells you how much you should work to improve your training set performance. And And by the way, this is one of those things, the formula I wrote up just now, right? If you can rule out half of all possibilities, focus on bias or focus on variance or vice versa, that's really doubling the speed of productivity, right? If you can rule out 50% of things you could work on as less useful, I mean, that is like a 2x productivity gain for your team, right? Let's see. So, all right. Let's do a quiz. This is a tutorial. So bearing in mind the motivations I gave just now for why human level performance is useful for driving machine learning progress, let's say that you're working on a medical imaging example. Right? So, look at a medical image and diagnose a medical condition. And let's say that a typical human has 3% error. So if you or I, as a non-medical specialist, right, look at the images with a little bit of training, you and I would make, maybe the non-doctors in the room would make 3% error on this task. Let's say a typical doctor makes 1% error. A highly experienced doctor makes 0.5% error in the diagnosis. And a team of experienced doctors makes 0.3% error. Okay? So the question is, how should you define human level performance? Why don't you think about this for a second? Okay? So for the purpose of driving, so you're working on a medical imaging diagnosis problem, and you want a definition of human level performance to plug into all of these analyses you're doing. Is it 3%, 1%, 0.5%, or 0.3%? Right? Actually, there. This makes the official multiple choice. All right, are you ready to vote? Who thinks A? Very few people. Who thinks B? More people. Who thinks C? Oh, cool. There's like who thinks D? I see. Wow, cool. Okay, awesome. Right, you guys are good. All right, good. I agree. Interesting. Last time I ran this quiz, almost everyone got it wrong. The majority of you guys are right. Yeah. And just to summarize, I think to the extent this is a proxy for Bayes' error, right? If a team of experienced doctors can do this, it's just closest to Bayes' error. So for speech recognition, we surpassed the performance of a single person like a year ago. And so today, for speech recognition, if we're trying to compare the performance of algorithm, we routinely get a team of people together and sit and debate, and then we actually benchmark ourselves against that. And it looks like we're often surpassing that as well, which is a problem. It makes it harder to keep making progress. Okay. So let's see. How am I doing for time? All right. Let me say a couple things about future of AI, and then I want to talk about AI and product management. Right? So, one of the questions I get asked a lot, and that I guess you might get asked as well, is what does the future of AI look like? Right? What does future of machine learning look like? So again, from an application perspective, in terms of what's shipping and what's driving a lot of value to users, I would say that over the last, let's say 5 years, the value of supervised learning has really taken off, right? Okay, and maybe extrapolating to the future, I think will continue to be very important. I think that unsupervised learning is getting some traction. Maybe it'll take off. Maybe it'll continue to take off in the future. And I think the number one application of unsupervised learning these days is word embeddings, right? Maybe. Really started by Yosha Benjo long ago, Colabert Western did a lot of work, then there's Glove, Word to Vec, so those models are very useful, but I feel like more and more traction. I hope that reinforcement learning will take off in the future as well. Well, maybe they'll spike like that. Who knows what the future is like? It's very uncertain. And I'm actually quite confident that AI will keep on improving, actually. We've had a few AI winters, so is it possible that it's about to do that, right? And I think the answer is no. And there are two reasons for that. One is just the sheer scale of investment, just a number of great researchers all around the world, trying to invent new ideas and creativity, that's one. But the second, more concrete one, is that when I look at the problems we face today, when I look at the roadmaps of the microprocessor companies, more than one of them, multiple hardware companies I feel have credible and specific roadmaps for driving better computational performance. And I feel that I see enough problems that today are still bottlenecked by computational speed. So my prediction is that over the last 5 years, one of the huge drivers of AI progress has been computational scale. Well, raw data just need a way to process it or need a way to experiment with algorithms. And one of the reasons I'm confident that AI will keep on having this explosion of creativity is because I've seen the technology roadmaps of multiple of these hardware companies, and I feel confident that we have specific and credible roadmaps for bringing faster processors, faster networking, faster hardware to bear. And I'm quite confident that faster computation will keep on driving these curves up and to the right, especially on supervised learning, which is very bottlenecked right now. I think that a lot of people ask, right, after supervised learning, what's the biggest value driver, unsupervised learning or reinforcement learning? I've been looking around the things we're doing at Baidu, and to less extent other companies. I think that there's actually one gem hidden in there that will be the next driver of value that's not unsupervised learning or RL. Even though I love unsupervised learning, I think about it quite a lot in my spare time, try to research. And that's transfer learning or multitask learning. And this is already happening. Just like back in 2011, supervised learning was already happening, but I thought it was going to take off, so we started investing in scale to drive that. Right? And today, this is already happening, but I see its value rising very rapidly, so we're investing in this as another driver of value. But as a concrete example, in computer vision, we routinely pre-train a model on ImageNet. Take AlexNet, one of the later ImageNet competition winners, right? And train a model on a classification, right? And because you have a lot of data from ImageNet, you can then lop off this last layer and plug it into something else, right? Onto some other application you care about. I don't know, whatever. Let's say self-driving, right? As an initialization for some other neural network. So I'm seeing this transfer learning. We learn from one data set with a ton of data to pre-train a neural network for different related tasks to be very valuable for more and more applications. So I would actually predict in the next few years that we'll see a lot of concrete value driven through transfer learning. Transfer learning is usually when you have one problem with a ton of data and you want to transfer that knowledge to a different problem with maybe a much smaller data set. There's also some multitask learning if you try to do 10 tasks at the same time and they all help each other. But multitask learning tends to be more valuable when you have 10 tasks with maybe comparable sized data sets. So I'm seeing somewhat more work in transfer learning than multitask learning. And I think all this is very much see the pens as you're making, and there's still a lacking theory to be worked out for all of this as well. Yeah, I think we need much better theory for transfer learning and multitask learning, right? Yeah, but I think, well, today in computer vision, we use this a lot. Oh, and maybe just one thing, I mentioned training on ImageNet. one thing you'll find is that the bigger the data set you have for the task you're transferring to, the better. So within Baidu, with some image data sets that are way bigger than ImageNet, right, both in examples and the number of classes, and we just find that when you train on way bigger data sets than say ImageNet, the pre-trained network actually works much better as well, right? So that's another trend. It's allowing us to train on really, really big data sets and use that to transfer the data, transfer the knowledge to new tasks. We do this for text-to-speech as well. Train a lot of data, then train on a new specific TTS task you want. We do this on speech recognition, train on Mandarin Chinese, and then take the trained model and train it on a low-resource language, like Cantonese, where much less data. But this is already actually working very well. It's just maybe unsupervised learning and RL are sexier, so people talk more about that. But I'd say supervised learning is creating most value by far, and transfer learning, not nearly as much. It's a very, very distant second, but it's already shipping in quite a lot of our products. But I feel like a lot of this is ad hoc, without a theory that tells us kind of systematically how to do it. Okay. All right. The last thing I want to do is take everything we've talked about and wrap it in a bigger framework of how do you actually use this to build useful products, to build useful applications. And to make an analogy to the rise of software engineering, product management. Oh, I'm curious, how many of you know what a product manager does? Oh, interesting, like a third of you. Okay, cool. Let's see. So, this is very interesting. If you pull up an app, right? Let's say I fire up the Facebook app. Someone had to make a lot of decisions about how to write the app. Like, where's the social media sharing button? Does the feed scroll when you swipe up versus swipe down? How big is the picture in this app versus that app? How big is the logo on top, right? So someone, a product manager, had to make all those decisions about how to write that app. And what happened in the history of the software industry was first came, computer programmers, so we would write software. We could write software to do almost anything. But then we realized that a lot of the software we wrote wasn't what users wanted, right? And so over time, the software industry evolved to have this job called product management. And the workflow, I'm going to draw a simplified cartoon version, right, is this, where a product manager is responsible for figuring out what products users really want, how big the size of the image, how important is latency, how important is whatever. And then the product manager communicates with engineers, with software engineers, how to design the app, right? And so the product manager would communicate to the engineer a specification, right? So actually, for example, for the Baidu search app, the product manager might tell the engineer, I want to write an app where there's a logo here, and there's a search bar here, and then there's a news feed here, and there's a button here to do whatever, right? So the product manager will design a wireframe and send it to the engineer, and the engineer can then implement this. And this division of labor is pervasive in the software industry today because we found that rather than having every engineer talk to users to figure out what users want, it's just more efficient to send product managers to figure out what application designs users most want, and then summarize those conclusions to the engineers so the engineers can focus on doing the engineering. Okay? For those of you that are purely in academia, you might not be used to this workflow, but I find that a lot of engineers are very grateful to the PMs for helping figure out, if you're doing engineering, where should this button go? I don't know, but hopefully a product manager can go figure out those things for you. Okay? So where this fits into AI is that with the old era of software engineering, a product manager could, hand draw almost any app, right? And we know how to build apps. A product manager can draw an app. If you're building an app like Facebook or Snapchat or whatever, product managers draw up the design, and we could probably implement it. It's just a matter of how long it takes and how costly it is. But with AI tools, it's a different game. The things we could do with machine learning is very different than the things we could sort of do with just building applications. And so one of the things I'm seeing is that the practices for how to define products, for how to design products from the perspective of product manager is also changing. So here's a concrete example. Let's say you're working on a speech recognition algorithm. What do you want to focus on? You could focus on improving performance of speech recognition in noisy environments. And noisy environments could mean car noise, it could mean cafe noise. Or you could work on improving performance on low bandwidth audio. Right? Or you could work on improving your recognition on accented speech. Or you could work on improving the latency of your algorithm. Or you could improve on maybe the binary size. Right? Turns out if you're writing a mobile app, the binary size really matters because users don't want to download like a 2 gigabyte image onto your cell phone, right? So you, as an AI scientist or an AI engineer, you could work on all of these things. And the question is, what should you focus your efforts on? We live in a world of limited resources. You can't, if it goes to publish a research paper, you could pick almost any one of this, work on it, and write a paper. But if it goes to ship a product and do something that helps hundreds of millions of users, then I don't know. Which of these should we focus on? So it's the job of a product manager, in most organizations, to go and figure out that, gee, for this scenario, please focus on this, and don't worry about those, right? So I think product managers can really help us prioritize. And I feel like in machine learning, there are just too many ways to improve any concrete machine learning system and we don't have time to do them all. So product manager really helps with prioritization. Maybe one way to think of a product manager's job is, there's some fuzzy set of what users want, right? And then there's some fuzzy set of what ML can do. So you, as a machine learning engineer or scientist, you might have a vague sense of what this rightmost set is. And it's a product manager's job to figure out what is this leftmost set so that together you can hopefully find something that's at the intersection, right? Something that users want and that you can build. So in the old era, we would have PMs write wireframes, write PRDs, or product requirement documents, and send to engineers. In the new AI era, I find it's been exciting to try to figure out new practices for how a product manager can communicate to us, the engineers and scientists, what to try to build. So you can't wireframe a self-driving car, right? And it's just the old practices don't work. So here's one thing that here's one way of dividing up PM responsibility. Right? One of the very good ways for PMs to communicate with scientists and engineers is that the PM provides dev and test sets and provides an evaluation metric, such as accuracy or F1 score or whatever the product manager thinks matters most to users. And by providing a dev and test set, the PM can express. The PM can put lots of accented data in there, or they can put lots of noisy data in there. But this is a way for the PM to express what is the data that's most important for you to do well on. And then I think the engineering or the scientist or engineer responsibility is to acquire the training data. And I usually assign this responsibility to the scientist or engineer because we can do things like synthesize data or crowdsource data or innovative ways to get more data. And then, get system that works on the dev and test set. Okay? So it's very interesting, only about a third of you work with PMs. But if you're working with PMs, sometimes, even today, I find that PMs come to scientists and engineers with suggestions that are very hard for us to implement. But if you, one of the things we did, actually, is Eloise, are you around? Eloise, if you're around, could you bring me a copy of the handout? One of the things that, oh good, come on up, Eloise. One of the things I did was, if you're wondering why I use a whiteboard, it's not that I'm too lazy to make slides. I did make slides, and we even printed them out for you to pick up at the end of today. But one of the things I did was put in the slides we printed out, this thing in exactly one slide, so that if you work with PMs, hopefully you can hand this to the PM and say, Andrew says you should do this, and this will actually make your life easier for how they communicate with you. Just to finish up, boy. All right, I'll say two things. I'll wrap us in around time. You know, since I taught the Coursera machine learning MOOC, thank you. This is Eloise. She works at Baidu. And I'll tell you in a second what this is. Since I taught the Coursera machine learning MOOC, the most common question I get asked these days is, how do I get better at machine learning and deep learning, right? Even beyond the Coursera MOOC. And I think that hopefully many of you, right, through coming to NIPS, have a basic sense of machine learning and deep learning. I just want to give you two pieces of advice. One is that I think too many people, you know, there's a very repeatable PhD student process that we use at Stanford and to turn people into great researchers. And I feel like it is this. Read a lot of papers and replicate people's results. Right? I think that the temptation to do your own thing is very high, but sometimes you're actually better off focusing on replicating other results rather than jumping too soon into inventing your own new thing. And the other thing I want to share with you is almost all the work we do results when you look at what we do minute to minute in dirty work, right? When we build a speech system, some of it is going out and collecting data or crowdsourcing thing or doing error analysis, looking at examples one at a time. When I was working more on robotics, sometimes what I had to do was get in my car and drive to a store, like drive to Home Depot and buy a piece of wood because that's what we needed. So almost all the glamorous things you see in machine learning results in dirty work. And if you're trying to improve your own machine learning ability, my advice to you is to make sure to do both of these things. If you do only the first thing, you know, you can, I guess, do academic progress, you can make some progress, you learn a lot. If you do only the second thing, you end up hacking and building systems, so you won't keep getting better. But I find that the people that become great tend to do both of these things. My advice to you is don't be afraid to do dirty work. Get the data, try out things, as well as keep reading research papers. And you know, when I wrote up the formula for machine learning, the Hail Mary was a new model architecture. And if you spend time doing this for, you know, many months, maybe a year, right, you will actually gain very deep intuitions about when you should plug in that new model architecture step that I talked about just now. All right, running out of time. So, been making this analogy, I speak to a lot of non-technical audiences as well, been making this analogy that I think AI, really machine learning specifically, is the new electricity, right? That just as electricity about 100 years ago transformed industry after industry, I think all of us, all of you, are now in a pretty good position to use AI to do the same. So I hope that some of what I shared today will help you develop more systematic processes for driving machine learning progress, and that when you go back to work next Monday, that you apply some of these things right away. At the back of this room, we have multiple stacks of handouts, which is basically a summary of everything that was said. So I did make slides. I just use a whiteboard and print out the slides. I'm not currently planning to distribute these in electronic format. Maybe I'll change around that later. But these are available in hard copy. These slides make sense only if you've heard this presentation, so that's why I've not posted them online. But but on your way out, please make sure to grab a copy of this and read through it so that you have a written copy of the concepts as well, including some slides that you might be able to show to your friends if you want to influence them. Like if your friend says, gee, I want dev and test sets to be different data sets, there's a slide you can show them that says, no, please do it this way. All right, let me just take questions for 5 minutes, and when people take off, please be sure to grab a copy of the slides. Thank you.
There are microphones if you'd like to ask a question in the aisles here. If you're leaving, please do so quietly. Maybe if I could start.
Sure, go for it.
I have a question. You made some forecasts about unsupervised learning, reinforcement learning, transfer learning. What about robot learning? Do you see this as something that's going to take off at some point?
Yeah, I don't know. Actually, sorry, yes, it's going to
Say
take
yes.
off. Yes. No, really, I think that actually one of the dangers of making predictions like this is I think we're healthier if lots of different people work on different things, right? So the stuff I'm excited about, it's actually better if different people are excited about different things so that we as a community can explore lots of different areas. I actually do think robots learning is very exciting. A lot of the work is done in simulation right now to give you enough data and let you run experiments rapidly. So I see a lot of rapid progress, at DeepMind, at Baidu, on various teams on robot learning, learning act-enriched environments. I hope that we'll start to migrate that to non-simulation environments as well, but I think the basic research there is very sound.
Okay.
Any other questions?
Yes, I have a question. Thank you, Andrew.
Oh.
So you made the distinction between a product manager in traditional software development and a product manager in machine learning domains. And so as a software developer, I've been interested in kind of marrying the two worlds and understanding how we can design products that leverage machine learning. And so one model would be to create the kind of the analogy of a plugin, an ML plugin that maybe has different profiles to plug into application architectures. I wondered if there are any thoughts that you've had behind that idea, or whether that has any legs at all.
Yeah, sure. Great question. Today machine learning needs a lot of customization. So I find that telling a PM, here's a software module that does machine learning, that's been less useful, actually, because almost every problem we work on just needs a lot of customization by an ML person. There is this rule of thumb I've been sharing with product managers, which is, and again, this is one of those oversimplified things that is an oversimplified version of reality, but I tell PMs, anything that a human can do with less than 1 second of mental thought, the typical human can do with less than a second of mental thought, we could probably automate now or in the near future. So that's been an oversimplified, frankly, definitely oversimplified, but useful role for PMs. And so today at Baidu, with PMs running around looking for tasks that they can do in a second as candidates for automation. And so, for example, we realize that you can look at a dish and recognize, is this, fried chicken or a burger in less than a second. So we recently launched an app that lets you review food. You take a picture, recognize what food it is, and then you can review the food in like a Yelp-like app, but the China version. There's much more, a lot of new features. And so that rule of thumb, less than 1 second of mental thought, has been one of the couple of heuristics we give to product managers. But in the end, AI is still so immature, they still need, for the most part, the close collaboration of the engineering teams, I think. Thank you. Is a question?
So maybe extending that idea a little bit more, if you have this idea that AI is the new electricity and is going to be distributed throughout the total company, how do you actually effectively interface with non-technical, like business managers or CEOs?
Sure. So I think that, so this is a kind of a, so let me make an analogy, right? Back around 2002, mobile was a big thing, right? None of us, we just couldn't hire enough mobile developers back then. Mobile was starting to be really hard. It was really hard to hire mobile developers. So what a lot of companies did was set up an organization, which was, the business unit, and then they had a mobile unit. Right? And the mobile unit would hire the mobile developers, ensure quality control, standardize work, attract the talent, and then they would interface with all the business units to figure out how different business units could move things onto mobile. And that was because mobile talent was so rare and it was so difficult. Now that mobile is everywhere, it usually doesn't make sense of a mobile unit. Instead, this unit's gone away, and there's mobile developers in all of the business units of a company. So I think we're in that phase of history where today it actually makes sense from an org structure perspective to have an AI unit and to embed AI members inside the different business units. And maybe the challenge of AI is that I think AI will keep on advancing for a long time. I think longer than mobile has, for complicated reasons I won't go into. But I think this org structure actually makes sense because AI talent is rare and needs to centralize. But then embedding them to the BUs and working cross-functionally is one of the challenges, maybe. Hope that, all right, I definitely was not expecting to be drawing org charts at NIPS, but there you go.
We have a question over here.
Sure.
Hello. Hi, Andrew. Question. What is your view on how will deep learning and AI progress in terms of detecting and classifying human emotions from images and videos? Also asking from the perspective of the data sets available and lots of noisiness and the human factor in the interpretation and so on.
Yeah, so there are a few organizations working on classification of human emotion from images. I think it works well. I think really, so long as it's a task that humans can do, I think that we have an excellent chance of getting machines to do it. I think humans today can look at facial expressions and classify emotions quite well. So for a machine to, in a few years, be able to read emotions as well as you and I can, I think that's well within striking distance. For it to read human emotions beyond what humans can, that might be harder, I'm not sure. But I'm optimistic about that. And noisy data, if it's random noise, usually learning algorithms do a good job averaging it out, so I tend not to worry about that. But if your data has systematic biases, like if a human systematically labels whatever, happy for unhappy or something, then the learning algorithm will learn those biases as well. Okay, thank you.
Let's take a question over here.
Yeah. Thanks, Andrew. I actually have a fairly related question. It has to do with human level performance. And it seems to me obvious in the reinforcement learning case, like playing video games, exceeding human level performance, that seems obvious why that's possible. But in the supervised case where the training examples are labeled by humans and therefore have all the noise of human labeling, it's unclear to me how a system would achieve greater than human level performance in that regime.
Sure. So, let's take medical imaging as an example. It turns out that for many concrete medical diagnosis tasks, like look at an image, diagnose breast cancer, tumor or not, even doctors disagree with each other, right? You show the same thing to 5 doctors, you get, several different answers. And so what we're seeing in crowdsourcing is just take a bunch of people and average their opinion, you do better than any one person. And I think that's one formula for doing better than human level performance. One thing I've seen in speech recognition is heavily accented speech. Different humans are actually better at recognizing different accents. If whatever, I don't know, boy, I was born in London, some people think of a slight British accent, the Brits don't think I do, but the Americans think of a British accent. So maybe I'm better at recognizing a British accent, and you're better at recognizing different accent and so on. And with enough data for enough people, we could see machines do better than any one human on average by exploiting the different verticals that different people are better at. So those are some examples, I guess.
A couple more?
Sure. I think, but let me. Should we take? Sure. Let's take 3 more questions. Should we take? Let's take those 2 and take a couple people here, and then maybe we should break. Do you want to go for it?
Hi, Andrew. I would like to know if there is some kind of framework or recipe, as the one that you presented now, to infer if the data itself has enough dimensionality. For instance, imagine that I choose to do some classification, use some set of features. Let's call it, for instance, HOG. There is some kind of way for me to know, okay, those features that I chose are enough for doing my classification job?
Sure. So, in the definition of human level performance, one element of that definition is to double check that the human is using the same information as the learning algorithm. So just now I used a speech recognition example where if I say, navigate me to Moscone Center, right? If a human has their knowledge that Moscone Center in San Francisco is spelled, Moscone, but the learning algorithm has never seen that word before. Then the human has extra knowledge compared to the algorithm, and you might think, well, how do I get this information to the algorithm? Maybe in the form of a language model. So when measuring human level performance, one of the things to double check is that the human is using the same information as what's input to the learning algorithm, because this guarantees, and no more information than the input features, because this guarantees that the human is just using some function mapping from input to output. Right? Another example, take self-driving cars. If you're trying to recognize other cars from LiDAR data, from laser data, but if the human gets to see an image as well as the LiDAR, then the human might be able to do much better just by the fact that they have extra information compared to the computer. Right? So that's what I would check. That's the question?
Hi. I just wanted to know if what would be your opinion on how to best validate your model, as in ensure that it's correct. So for example, you get stuck at the very first step of your methodology, where you see that your training error is high, and then you go and try different model architectures, you throw everything at it, and it doesn't budge. So how would you then debug it, like, from that point of view?
Great question. I think that, so long as you have the same inputs as a human, if a human can achieve a certain level of performance, then in theory, with a big enough neural network, with enough hidden units, you should be able to fit the data equally well, in theory, so long as your model architecture doesn't have certain restrictions, I guess. One other thing that works a lot, that I see a lot, is people reading papers and getting inspiration from the architectures in different research papers. Sorry, I don't have a more concrete suggestion than that. But the human mind works in an amazing way, right? When you read 20 papers and replicate 10 different neural networks, your brain will magically synthesize these 20 papers and come up with your own ideas for new things to try. That's just been a very repeatable process. So if you do that, I'd be surprised if you don't come up with some ideas. But one thing to double check, similar to the previous question, is to just make sure that humans can do well in that task given the exact same information. Sometimes I have seen be a failure mode for when you run into that problem.
Thank you.
All right, last question.
Yeah. Sorry, guys. Maybe let me just take one last question. I think we should break and give the room back. But sorry for apologies to everyone else.
Okay, good afternoon. My question is that is there any possibility to use deep learning in open-ended domain? I mean that whenever the number of categories or classes is not predefined and they are growing through the time. So can we use deep learning there or not?
Yeah, yes, you can, but it takes changes to the model architecture, right? So, for example, for the face recognition example, that is an example of open-ended domain where there's like an unlimited number of people. In fact, we register new people into our database all the time, and our system learns right away to recognize a new person because they learn a function that inputs two faces and matches them to tell if they're the same person or not, right? I think DeepMind had a paper on recognizing characters that was similar, kind of metric learning to look at two images and tell if the same person or not. I think it takes thoughtful design on the representation, because if you're an open domain, you have new concepts coming out all the time, so you can't assign one hidden unit to each new concept that might show up unless you retrain that one new output unit or something. But the things, the concepts like metric learning, where you compare to a reference in the database, that's been one technique for letting you add concepts and just measure if it's the same concept as something you stored away. But I think, I don't know, if you have learning algorithms with rich output spaces, actually for robot learning, I'm seeing some interesting examples where your learning algorithm is supposed to spit out a piece of text, and some interesting examples of when the text your learning algorithm spits out, when it's given the right training data, it can learn to recognize concepts that it hasn't seen in that context before. So with the rich output representations, I'm seeing some interesting work there as well. All right. I think we need to give the room back. So I apologize that we have to break. Thank you again. And do remember to pick up a copy of the handout on your way out. I think they're stacked in the back.
Thank you.
Thank you all, everyone.
Thank you, Professor Lee.